write it. That part of the Taylor formula is Taylor polynomial. That is residual term. Generalization, this classical formula, this is in 1D, 2, 3D, or in particular 2D, consists in changing geometrical objects from point in this formula to any drawing. Information on drawing about some functions, about behavior of these functions along drawing, and behavior its normal derivatives to m's order along drawing. Let us to write such in the form, such kind formula. If you let me, I shall write for two-dimensional case. The same variant like here. The same variant. But here, omega is m times normalized equation of the boundary of the drawings. Drawing can be any. And these functions have normal derivative in smooth points of drawing. First derivative is equal unit, and other are 0. In this formula, f sub o is behavior functions on the, or distribution functions on the drawing. Here is f sub 1, behavior first derivatives on the drawing, so on. This is normalizant, so f is And this residual term is quantity, small quantity, order omega in degree minus plus 1. But this formula can be used for any drawing, and of course in two-dimensional, of course in one-dimensional space. But we noticed that when omega is such functions. So omega is drawing of the point in two-dimensional case. In that case, this formula transforms in usual classical formula, Taylor formula for two-dimensional space. And if we consider in one-dimensional space equation omega x minus x, such equation of the point, this formula transforms into classical Taylor formula for one-dimensional space. But point in one-dimensional space is the simplest drawing. And there are a lot of one-dimensional problems where we must consider two or less or more than 2 points in one-dimensional space. So it is interesting to consider Taylor formula for 2 points or for several points in one-dimensional space. But use this formula to solving this problem is very difficult way. So I explain, suggest you generalization Taylor formula for 2 or more than 2 points in one-dimensional space. This way is very difficult. So it also leads to solution the problem. But so let us at first consider some kind lemma. Suppose in one-dimensional space, now we will be consider only that variant. Suppose that we have some interval and functions which is in point x1 is equal unity and is 0 in, suppose this function is h1, and suppose we have such construction, this function, that all derivatives in point in this point is equal 0 this function in that point is equal unity. And suppose in that point is equal 0 and all derivatives is equal 0 to. Such functions we can construct different ways. For example, we can use polynomial, such kind, or splines, or some other construction. I don't touch this construction, only suppose that such functions we constructed. Then, if I consider functions f of x, the same functions f of x, which have a polynomial Taylor formula, and if I multiply these functions on h1, and if I begin to construct it polynomial Taylor for these functions, we shall see for these functions. These functions is in point if I put instead x sub 1, then I receive the same, because this factor is equal unity. Then if I shall take derivatives, we shall have such construction. This is 0 if x is x1. So it will be 0 at this point, h will be unit, and we shall have so on. It is easy to see. So if I shall write polynomial Taylor for these functions, I shall have the same polynomial. h1x, fx, have the same polynomial and only new residual term. But this polynomial will be the same. But we see that h is go to 0 when we go to point to point. So suppose such picture, x1, x2, x2, and here is polynomial, Taylor polynomial for P, and polynomial, suppose this is Taylor polynomial for functions f and for for these functions. It is the same. But suppose when we consider first functions, behavior was almost the same, because we knew that Taylor polynomial can give us some kind of approximation. But this is suppose f of, but when we shall consider f multiply h1, we shall have here some kind of, but this will be graph. So these functions here almost the same, but residual terms for these functions will be very large. For this is Rm, this is Then suppose these functions be symmetrically continued, so this is x symmetrical point x1 minus x, this distance x2 minus x1. So yeah, this distance is, but if I want to be here, something it will be x2? No. 2x1 minus x2. And suppose I write once more time. x1, x2, this is one hill-like functions, and we multiply it, this unity, we multiplied it polynomial in first point, polynomial Pm in this point 1. But then the same constructions, shift these functions. Suppose it will be h2, this is h1, h2 is h1 x minus shift this function, and this multiply polynomial Pm2, and maybe third functions, so on. And now, if you consider the construction f h1 multiply polynomial 1 plus mh2 multiply polynomial m2, then these functions will be coincide with this polynomial in point 1, and in second point will coincide this polynomial in this point. So we can hope that it will be good approximation functions f, because these functions will have property first polynomial in first point and second polynomial. We consider the residual terms. So if I want to write exact property, I must to add some residual term for this formula. And this formula is in 2 degree n times lesser than for this formula. So in this formula, input information about functions f is 2 times larger for one polynomial and for other polynomial. We have in 2 times larger information, but residual terms in n degree times lesser. So we hope that these constructions will be useful for solving some 2-point problems. And of course we can continue this for third point. But when we begin to work with such constructions, we meet some problems with these functions, hill-like functions. This is function we consider as finite functions. I forgot to say that this is functions which is such kind, but further is finite. Problem is that if we're constructing these functions using polynomials or splines, then when we have derivatives, the differential property became worse after every differentiation. For example, if it's here polynomial n degrees, and after derivation is polynomial, and splines begin to have some order derivatives have uncontinuous. So we decided to consider we were trying to find these functions. Don't take it any form, but try to find such functions which will behave itself more convenient. So suppose we forget for what problem we consider and only put our attention on this hill-like functions. From the point of view of its derivativeness. Итак, suppose these functions, for simplicity, take interval from such kind interval and try to consider the functions which have such behavior. Is finite functions support these functions. Suppose this function is phi of x, but we don't know ahead what kind this phi f is functions. And we only know that in center is f is unit, and in this point is 0. And try to differentiate these functions. Then the graph of derivatives, first derivatives, will be such way. Here is 0, 0. When function is increasing, then this derivative will be positive, but in that point, derivative will be 0. So this will be functions with such kind of functions. Here, antisymmetrical functions. This is a graph with such functions. And shall try to choose these functions in such a way that this hill and this dip is the same form as these functions, only in 2 times narrower, and in some kind maybe higher or less. It leads us to the equations. Must be center, this function is left on the half. So here I must write 2 times nerve, it leads to 2 times 2 factor in for argument and shift to the left. But some coefficients we don't know ahead these coefficients. But for this dip, we shall have the same k. Yes, of course you are right. Only functions. So we receive such differential functional equations. Here argument is 2x plus 1 minus k f 2x minus 1. This kind of differential equation was unknown for us and unknown for those who working in differential equation with shifting arguments. So we could not answer about this equation, and after our self-investigation, we prove that if k is equal to, and only if, only in that case, this equation have unique solution. This unique solution we call such way up of x. These functions have very interesting properties. First of all, it is obvious then that if we shall take second order derivatives will be expressed among the functions, the same. So on. So, first of all, it is obvious this is functions such kind of infinitely time derivatives. Then let us consider what we receive when we take, for example, second order derivatives. Then for second order derivatives, in the same way, we receive that on this interval, function derivatives will be positive. On this negative, in this point row, here negative, and then positive. Such kind will be graph second order derivatives. But suppose we take this graph and shift it. Consider such and shifted such graph. This shifted graph will be such kind. This is a shifted graph. But if I add graph these functions and this function, then on that interval from 0 to half for 2 units, it will be identically 0 on
F2 штыка от x минус единица или x минус 1/2? Там же вторая как
я взял, I take this interval, and on all this interval, this and this give 0, and this give 0. So on this interval. But it means that f(x) plus f(x minus 1) is 0. From this we can say that f(x) plus f minus 1 is some linear functions on interval. But if we shall take derivatives more higher order, for example, some mth order, and begin to take a lot of different these derivatives, and with some coefficients adding, then we can receive that some kind of linear combination some order combination we can receive for any polynomials on any intervals. We can receive with such combination, linear combination, exactly is equal polynomial. So if polynomial, suppose have some graph polynomial, and any interval, any segment, then exists such linear combination that exactly coincide with this on that interval. But of course, some finite functions is become zero, become finite. If we take infinite number of combinations, we can consign polynomial on all intervals. But in any point, we will be differ from 0 only finite number of additions. So we see such very interesting phenomena. We knew that polynomials are have good approximation properties. So all theorems about approximation is true for atomic functions. This kind of functions, up-like functions, we call atomic functions. Then is some differ polynomials and such combination. If I change any coefficients of polynomials in polynomials, then I change all polynomials on all intervals. But if I change some coefficients here, I change only locally, only one such functions. So these functions, atomic functions, have property, good property which have splines, locally changing when changing one coefficient, and good property belong to infinitely times derivatives functions which belong the polynomials. So infinitely time derivatives and locally like splines. Approximation when using these atomic functions lead to matrices with a lot of zero because scalar product these functions, one atomic functions and the other, and other product atomic functions which supported donut intersections lead to zero. But when we're working with polynomials, we must construct special kinds of polynomials which have zero when we use when we in the product. That kinds of functions were constructed not only for polynomials, but also for polynomials which constructed from any functions which are solution differential equations, ordinary differential equations with constant coefficients. We knew that ordinary differential equations with constant coefficients, not only usual degree, but also exponents and sines, cosines, and so on. Such functions is their product. So for polynomials which constructed when we use exponents and cosine, such polynomials which you can use, and exponent multiplied sines, different constants. Such kinds of polynomials we can express from some kind of atomic functions. Not exactly up. Up functions is connected with polynomial, degree polynomial, such kind of polynomials. But for exponent and other, there exist some. This way, we receive new direction in our investigations. The main, that kind of functions was beginning from, in that year, on one of the seminar, I put the problem, state the problem, but at first years, it was without solution, but about after 1969 begin appear the papers in this, and main results belonged he has the same family as I have, and because he is my nephew. He is finished Moscow University, mathematical Andrei, and you knew this faculty, very good. So I finished my explanation about this direction. I only try to explain in what way this atomic direction connected with our functions. Our functions lead us to generalization to the lower formula. When we begin to working with this generalization, we go to the atomic functions. Next time, next lecture, I will be say about other kind of other direction, not our functions, but that direction also connected with our investigation in our functions and in atomic functions. In what way it will be? We knew that in developing mathematical developing, in the same time as appear different kinds of theoretical investigation appear, and new kinds of operations. In ancient time, we receive usual operations, multiplication, division, later sinus, cosinus, and so on, and in some way was natural choosing some operations which are useful in many situations, and some of functions go in left in past. These functions which we go through natural selection, through natural selections, are important, and we use them till now. But when we receive such kind functions, for example, or such kind functions, it is easy that they also will go through the natural selection, because they are very useful in geometrical problems. These functions, up functions, it is easy to see that will be useful in future. So now the using these functions is very narrow. And according to these functions, I must say that our academician, Nathan Bernstein, about 60 years ago, said that maybe in the future mathematics natural way will go to infinity time derivatives, but not analytical functions, will be in theory of functions, play a role as important as, for example, numbers A and P in theory of numbers. It seems that these functions is answer for his predictions, such kind functions. They are infinity time derivatives, but not analytical. If I shall try to write series, degree series, for example, in that point, series for functions up will lead to such functions. In that point, it leads to such functions, so on. In some points, it will lead to second degree. So these functions don't express in any degree the areas which is coincident with these functions, even in small intervals. So this function is not analytical in any point in their support. Here, of course, is analytical, 0, but in other points is not analytical. And these results, new functions which we receive, and they now or in the future will be useful, will go through, lead us to special searching maybe other functions also that kind exist, but we don't know them. And it leads us to consider from the very beginning, from the operations, in what way we took exactly this addition, because we have fingers and use them in addition. But we knew that, for example, in special theory of relativity, there is another addition for velocities, which have another formula, not usual addition. And maybe we can, using new addition and new, from the very beginning, will be constructed new calculus and receive new operations, which we also lead us to interesting results. So next time I shall lecture about some kinds of uncalculus, non-Archimedean calculus. Now, if you remember, I several times consider some problems. For example, we consider a problem when we have two conductors. Here is functions 1, on that left part -1, and satisfy the solution of Laplace equations. I asked Professor Tanya and Igor to solve this problem using Toshiba, which Vadim Shapiro presented us. And then consider when we shall use our system programming, which in their base have our function theory, when we can changing the solution. At first, will be this problem. Then we shall transform this problem in such way. Take some straight line, and instead of this point where solution have jumping, have continuity. But for example, in any other points here and here, which we input give 2 points. We give 2 points on this straight line, and automatically here it will be -1, right, +1. Then we put in some domain not this medium with different properties. Here will be conductive with one kind, here will be 10 times, for example, higher, or any times higher. And then consider the same problem. I also show you such example, and we take instead of this such and jumping derivatives. Here will be -1, here +1. And you have various these programs. You must take this program. On this page is program for solving all this. I have some comment. You can see several parts, several pieces of this text. Declare, this is about information, split P1. This means that we shall use undefinite component, we shall approximate by splines. Name this indefinite component P1. Next, band X. Band X, this is strip parallel X. This is primitive such strip. Band such strip. Name F1, F2. And line, this line, have name F3. What kind of strips we shall have, we shall use, or what kind of line? It is explained in last absatz when we shall consider value. Second absatz, omega. This is information about our equations, about functions which we use for writing equations. For example, omega O is F1, one strip, and intersection with F2. This information that these two strips give us the rectangle. Next one, this is formulas which I explain you how to write equation of the part of the such formula. F, when we from drawing F is equal 0, take part which belong to the domain field more than or less than 0. In that kind, you will see squared WO is multiplication. This is WO. This is square. These functions F. Then such sign is equal this disjunctions, and F3 minus F3, this is left part of this line F3. This is all information about geometry, and this construction the system realized using our functions. So on. In the cursive, we can see this is the problem. What kind of system we must to solve when solving this problem? This connected with Laplace equations. When we minimize the functional, it leads us to this system of. And now you can see the solution. This is a solution of this function. You can see that in this point, when we shall consider more only behavior, only vicinity of this point, we shall receive some maybe some kind of bad behavior. So we consider our construction is these functions which we have, which we satisfy boundary condition, and then omega is for all rectangular, and this is polynomial with a spline polynomial, in our case, with undefinite components. But we shall consider now what look has this spline polynomials on this, in this domain. Instead of polynomials, only undefinite components. No, further. This is all. So when we consider this undefinite components, we can see that in this point, these functions, undefinite functions, have a small jumping derivatives. So how to avoid this, how make solution more exactly, we can consider more large construction. For example, using in vicinity of this point, construction such kind. Arc tangents. These functions is satisfy Laplace equations, but when y is go to when y is go to unity, go this point unity, the arctangent go to p divided 2, and we receive, this is go to such jumping functions which we wanted. When x is positive, it go to the 1. When x is negative, it go to the -1. And due to this, we can, in here also in this way, if we use this information, we can slightly correct the solution. But another way is take much more order splines approximations. Yes. The functions P, these functions. This, slightly corrected, but it is very hard way to receive almost exact solution. If we consider practice problems, then further solution which we receive is good for them. But for those who wanted to receive as exact solution as only we want, then we begin to think what in what way to throw out this this slightly noticed bad behavior. Now, let us change the problem and, for example, consider some situation that we take arbitrarily these lines. One example. He is in the 3D information. You can see that such changing lead us to changing the solution, approximate solution, but in any case we receive good results. But now we shall consider this example. In this program, also medium, some kind of medium here. In this program, only one line will be changed. When we want to put here in recursive function something changing very little. And we receive, for example, this, in what way we changing the results. This is three-dimensional. Now, this is the same, but for different lines. So, using light movement of the hand, we can go from one problem to another problem, which differ from one from another. Легким мановением в руке, я сказал. Легким мановением в руке, я сказал. Now, what we must to change in this program when we can use this domain instead of rectangle? Only in absatz omega we changing, and declare we use another primitive function, sinus and circumference and line, and 2 or 3 lines changing lead us to the solution of this problem. You can see. Go on. Another sections. Go on, go on. Also. Now, another examples. We consider, no, another example. We consider now, we show you some problems, more high-order differential equations, which maybe you meet, plate problems. Plate shall have different configurations, different kinds of restriction on the boundary in different positions. So we shall show you, you see several different domains. But we, on one of the lectures, you could see that this different, for example, for finite element method, from our point of view, is the same method, the same domain, which only differ input parameters, geometrical parameters, which parameters. This is all kinds, this is domains from the same family boundaries. Go on, дальше. You can see that this solution for different kinds of restriction. For example, here is in this example restriction is in right higher point and on the bottom. But changing restriction lead to different solutions, and I only think that we show you them. Go on, продолжайте. So I finished my telling about our functions, and next time I said what we shall consider. Thank you very much for your attention. Maybe you have any questions.